Welcome back to part 5 on reciprocal functions. We have y equals 1/2 cotangent of 2x plus 1. The amplitude is 1/2. The period is going to be a standard cotangent period, which is pi, divided by 2. The interval will be found by taking a standard cotangent period, which is on the interval from 0 to pi, and put 2x in between, and then solve for x. So we'll divide everything by 2, and we get x is between 0 and pi over 2. So our interval is between 0 and pi over 2. The phase shift is not applicable since we haven't been shifted to the left or right, but we are asked to shift up 1 unit. My domain is going to be all real numbers except for x cannot equal n times pi over 2, where n is an element of the integers. And the range is going to be from -infinity to infinity. Now let's go ahead and sketch this on the interval from 0 to pi over 2. Notice that I could also have additional intervals to the left and to the right at multiples of pi over 2. 0, pi over 2, pi, negative pi over 2. You get the idea. Now I'm going to quarter my interval. Between 0 and pi over 2 is pi over 4. Between 0 and pi over 4 is pi over 8. And then 3 pi over 8 on the other side of pi over 4. This takes some practice to get used to how to break up your intervals. And since our amplitude is 1/2, I'll go ahead and label the 1 and the 1/2. -1/2, -1. And now I need to sketch an approximate graph. I know that before I shift up or down, the period for one cotangent will start on the leftmost side, approaching positive infinity as I get closer and closer to 0 from the right. The curve will cross at pi over 4 and become negative and approach pi over 2 as the curve goes closer and closer to -infinity. But I also know that instead of being at 1 at pi over 8, it's actually at 1/2. And at 3 pi over 8, it's going to be at -1/2. And so I can sketch an approximate curve here. And I can sketch a whole bunch of additional repetitions of the period because this does repeat. But I have forgotten one very important thing. All these points are shifted up 1 unit because of the +1. So I take whatever I had as a point and I shift it up 1 unit. And so I make my curve, but shift it up. And so my repeating periods of cotangent looks something like this. The next equation we need to graph is y equals tangent of 4x plus 2 pi. If we take the guts of this tangent function and we look at the fact that we have a 4x plus 2 pi, we know that shifting a tangent function by 2 pi is equivalent to just leaving it alone. So what I'm going to do with this function is I'm going to assume that it's been shifted 2 periods to the left. But other than that, I'm not going to worry about it too much, because remember, if you add a period to a function that is already periodic, it does not change the function. So we can say that this is equivalent to tangent of 4x. The amplitude is 1. The period is going to be pi, because that's a standard period for a tangent function, divided by k, which in this case is 4. If we want to find the interval, or the starting and stopping point, for tangent of 4x, we take 4x and we put it on a standard interval from negative pi over 2 to pi over 2. And then we multiply everything by the reciprocal of 4. And that will give us my new interval, which is a horizontal shrink. So it'll be negative pi over 8 with x in the middle. So x is between negative pi over 8 and pi over 8. Now I need to look at my phase shift. We already talked about the phase shift. Technically, we'd be shifting to the left if we left the 2 pi in, but I'm going to say, since the phase shift was 2 pi to the left, it's equivalent to just not applicable. If you really wanted to figure out where that interval was shifted to, even though your tangent is graphed beautifully and there is a period for tangent about the origin, you can take the original function and solve for x in this interval, and you actually get negative 5 pi over 8 to negative 3 pi over 8. That's actually where the original period gets shifted to. But since the periods continue on forever, we can just graph one of them and make it easier. So my interval is from negative pi over 8 to positive pi over 8. I break my interval up into quarters. And I sketch the tangent. The domain for this is going to be x as an element of the reals, where x cannot equal n pi over 8, where n is an element of the integers, and n cannot equal 0. And the range is negative infinity to infinity. In this last equation, we have y equals cotangent of 2x minus pi over 2. If I factor out a 2, I'll have 2 times x minus pi over 4. So my amplitude is 1. My period is pi divided by 2. My interval can be found by taking the standard cotangent interval from 0 to pi and plugging in the guts of the cotangent. So 2 times x minus pi over 4. Dividing everything by 2 will give me 0 is less than x minus pi over 4, less than pi over 2. Then I can add pi over 4 to all three pieces. And I get pi over 4 is less than x is less than 3 pi over 4. So my interval for this function is going to be from pi over 4 to 3 pi over 4. My phase shift is to the right. Pi over 4. The domain is going to be on intervals from pi over 4 to 3 pi over 4, and the range will be negative infinity to infinity. Let's go ahead and graph this. I've gone ahead and quartered off my interval. I have pi over 4 as my asymptote, 3 pi over 8, pi over 2, 5 pi over 8, and 3 pi over 4. I know that the cotangent function does something like this. And starting the top left, crossing over the x-axis, and heading toward negative infinity as it approaches 3 pi over 4. I also know that the cotangent is 1 at 3 pi over 8 and negative 1 at 5 pi over 8. So, and it's 0 at pi over 2. So I know that I can just connect the dots. And that is sufficient to sketch that graph. Lastly, we can list our domain as a set where x is the real numbers, an element of the real numbers, such that x cannot equal, or where x cannot equal 2 times n minus 1, that gives you all the odds, times pi over 4, where n is an element of the integers, or n is in the integers. I hope you're getting comfortable with this notation. It's really quite cool once you get the hang of it, but I agree that on occasion it can be a little overwhelming if you've never seen it before. It will come up again in calculus most likely, and it does help to be at least familiar with this set notation.